Hi, my name is KJ Hardrick, and I'm representing Team 15, and this is our final challenge briefing. Just to give a general overview of what we're going to talk about today, we have four main things. It's the race challenge, Pure Pursuit 2.0, obstacle avoidance, and experimental evaluation. And then we'll get into the various things that fall under those umbrellas. So right now, I'm going to hand it off to Sam to talk about the race challenge.
So on to the racing portion of the final challenge. We first started by reading up on racing line theory, and we found that it's fastest to take the widest turn radius around the turn because this is going to allow us to have faster velocity around the turn. We also found that it's preferable to typically take the late apex from the turn, which is illustrated by this green line, because this is going to allow you to have higher speed into the next straightaway. However, we opted just for geometric turns, which is just this yellow line, which is essentially a circular arc. And we opted for this because it's going to have good performance on sections of the map where there's many turns in quick succession, and it's also much simpler to implement than a late apex turn. And so in order to create these trajectories with geometric turns, we needed an efficient way to do this. So we created a script that helped us facilitate trajectory generation. And essentially, it requires some user input. The user needs to click 2 points to define a line for the first straightaway, 1 point to define the apex point, and then 2 more points to define a line for the second straightaway. And then a circular arc is going to be computed that's tangent to both those lines and passes through the apex point. And this is repeated for the entire trajectory to give us a trajectory that looks like this. And as you can see, the trajectory is very smooth, which is really favorable for our Pure Pursuit controller, but also the turns are taken at the widest radius that they can be while avoiding collisions. Now, for actually racing on this trajectory, we want to be taking straightaways with a bang-bang controller approach. This means we want to be accelerating as much as we can until we reach the breaking point, where we want to be deaccelerating as much as we can until we reach the turn. And then on the turn, we want to be taking a constant speed. And this speed is going to be determined by Newton's second law. We want to be taking the highest speed possible that's allowed. And in order to figure out what the speed is, we first needed to derive the centripetal acceleration of the car. And we did this by taking the car on a turn and increasing the velocity of the car until the path that it took was aligned with the radius that the trajectory was generating. And from that, we can figure out the centripetal acceleration by A equals V squared over R. And now that we have that, we can use that constant to figure out what the maximum velocity is for any given turn on the trajectory. And so the trajectory script is actually going to automatically figure out the velocity and attach it as a waypoint to the very start of the turn. And it's also going to attach another waypoint to the end of the turn. And so as the car is driving, it's going to be on a straightaway, it's going to be accelerating as much as it can, but it knows that when it reaches the turn, it needs to be going at the velocity dictated by the turn waypoint. And so we can use kinematics to figure out what the minimum braking distance is as the car is traveling based on its current speed and the turn speed and the linear acceleration, which we experimentally determined. And so the minimum braking distance is illustrated by this yellow box. And essentially after this distance is greater than the distance to the next turn, that's when we know we need to start deaccelerating so that we can reach the target speed at the turn. And so that's how the speed control and trajectory is generated. Now on to Lisa to talk more about the details of the Pure Pursuit controller.
So the Pure Pursuit algorithm is very similar to the one that we coded up for Lab 6. However, we had to change a couple of significant things in order for it to work in the new race car simulation. As a quick review, the Pure Pursuit algorithm works by first identifying the robot's location with some type of particle filter localization. And then secondly, it finds a point on the trajectory that is closest to the robot. And then from that point, it finds a goal point that is a certain look-ahead distance away from the robot. Finally, the robot calculates the curvature of that trajectory and the desired steering angle the robot needs to take in order to reach that goal point. So in order for our Pure Pursuit algorithm to work for the new race car simulation, we had to make a couple of different changes. So the robot still had to localize itself, and we used the staff solution for Monte Carlo Monte Carlo localization. After that, we had to build the trajectory using waypoint detection. That includes waypoint detection, as Sam outlined. After that, we still have to find the path point closest to the vehicle and then find the goal point that is close to that path point. The main difference here is that depending on if we were on the straightaways or if we were approaching turns, we approached this differently. On straightaways, we adjusted the look-ahead distance to be a function of both speed and curvature. This meant that the look-ahead distance got larger when our velocity increased, and it got smaller as our velocity decreased. This is different from how we made look-ahead distance a function of purely curvature in the last lab. Okay, so after that, we calculated the desired curvature and the steering angle to get the robot to that goal point. And around turns, we hard-coded specific speeds for the robot at specific waypoints. This was in order to prevent crashes and was also necessary because in the robot simulation, the robot took a certain time in order to accelerate and decelerate from desired velocities. So now onto KJ to talk about the obstacle avoidance algorithm.
So now that we know a little bit more about the pure pursuit algorithm used, I'm going to talk about how I used that and our previous safety controller to implement a fast obstacle avoidance algorithm. So the overall fast obstacle avoidance algorithm is based off our safety controller model that detected collisions in the first place. Our safety controller was able to successfully detect obstacles, while our pure pursuit model could successfully and quickly follow a trajectory. So combining both of these would ensure a quick, fast obstacle avoidance algorithm that works. And to recap of what our safety controller was, it involved using our LiDAR data scans and would try to find the next point that the robot would travel to. And we would find that with the displacement equals this maneuver constant times b. We could vary the maneuver constant depending on how far we want to look ahead and how cautious we want our car to be. So that's something that we tuned, and I'll talk about that later on. In terms of the maneuver time itself, maneuver time is something that I varied while trying to implement this fast obstacle avoidance model. We used the vehicle's current velocity and the distance we expect the car to travel to determine our maneuver time. And the way I was able to find this overall distance that the car is expected to travel is using the physical dimensions of the car. We're able to calculate the overall turning radius, and a fraction of this turning circle was the distance that we used. And overall, to implement this with a Pure Pursuit 2.0 algorithm, we were able to just use the same existing code and morph it into a file that included both safety controller implementations and the Pure Pursuit algorithm implementations. And whenever an obstacle is detected, the car will slow down and either turn left or right depending on the side of the obstacle. And after that maneuver time seconds, Pure Pursuit will take over again and the car will go back to its original trajectory. The way we tested all of this was very experimental. We had a lot of parameters that we had to tune, like min look ahead, maneuver time, maneuver speed, just various parameters that changed how quickly our car reacted or how quickly it would take turns. And we just had to optimize this to, one, still go fast, and two, not run into things. So we did this by logging the results of each parameter, and we were able to optimize the parameters to fit our needs. So this is a video from our initial obstacle avoidance testing. As you can see, it was not perfect and would slow down but wouldn't fully turn and kept hitting different objects, and ultimately it didn't even properly maneuver around this last object and got stuck. So by varying various parameters, we get into our later iteration that we used for the final challenge. And now, one, it's less jittery and is able to more quickly avoid some of these obstacles. And so we were able to just fine tune it from there and see how things improved. So in conclusion, this was an overall good experience putting together various pieces of knowledge. We had regular labs throughout the semester, and it was really cool learning how to deal with the actual car dynamics, which was just overall interesting challenge. Fine-tuning a system takes many iterations, but the end result can ultimately be worth it, even though it takes many, many hours to try to fine-tune some of these things. And yeah, that was our final challenge briefing. Thanks for listening.